Right, this is part B of the CIE March 2022 mechanics paper. So I worked through questions 1 to 4 in part A. So we're going to complete that by doing 5 to 7. Okay, so here we go. As I mentioned before, I won't work through the calculations in detail. You can pause the video and satisfy yourself of the calculations if you wish, but really just want to focus on some of the principles and the techniques for solving these things. So number 5, 4 coplanar forces act at a point, and the magnitudes of the forces are 10F, G, and 2F as shown on the diagram with these angles. Given that the forces are in equilibrium, find the values of F and G. Okay, so this, I'm assuming that you kind of know about resolution of forces. And another theme that comes into all these A-level questions is simultaneous equations. Right throughout A-level, forming and solving simultaneous equations crops up all over the place, and particularly in mechanics, and particularly in these kind of problems, actually, because as you can see that F is relevant in both the horizontal and vertical directions, as is G. So that's where we're headed with this one. So if we just look at the vertical forces on this, we can map this out sort of G sine 60, which is the resolved part of G upwards, plus the resolved part of this one upwards, 2F sine 40. And that's going to equal to this 10. Then we do a similar thing in the horizontal direction. That's G cos 60 going this way, plus F is going to be equal to the resolved part of this 2F through this 40. So that's going to give us this equation. Right, well, at this point, yeah, we've got two equations in two unknowns, and it's a principle, it's relatively straightforward process to just go through and solve for F and G. I've done that by isolating G and this sine 60 and G cos 16, dividing one by the other, and kind of working it through on that basis. So that's eliminated G for me. Just one thing I would say is that you have to be very careful. It's very easy to go wrong with these kind of calculations, and so yeah, just a bit of care is needed. But if we work that through, and you can pause the video and just assure yourself of the fact that F comes out to 4.53 newtons, and then if we substitute that back into equation 1, this first one up here, then we're going to get this, and that result comes out to 4.78 newtons, two decimal places. Okay, so that is part A. Then he goes on to say, given instead that F equals 3, find the value of G for which the resultant of the forces is perpendicular to the 10 Newton force. Right, okay, so sometimes the approach is not totally straightforward, but what you're being told indirectly is that if it's perpendicular to the resultant force is perpendicular to the 10 Newton force, then the resultant force in the vertical direction, so all of that resultant is acting in the horizontal. So the resultant in the vertical direction is 0. Okay, so so that kind of idea comes into a few questions in different forms, obviously. So, but we can use that here. Resultant force up, down equals 0. So let's just write out those forces there. Yep. So we've done the same thing as before, written that out. And then we can just go through and calculate G. So we know what F is. So we've just got equations in G. And that works out to 7.09 newtons to two decimal places, which I should write in there. Okay. All right, so that is that one. Say the principle's not too difficult. It's a little bit of a trick here with the resultant force, but kind of really the main difficulty on this one is just making sure you don't make any mistakes with all this calculation going on. Right, let's move on to this next one. A cyclist starts from rest at a fixed point O, moves in a straight line before coming to rest k seconds later. The acceleration of the cyclist at time t after leaving O is a where the acceleration function is this thing here for t between 0 and k. So find the value of k. Right, okay. So so what we're interested in here, moves in a straight line before coming to rest k seconds later. So coming to rest. So coming to rest implies velocity. We haven't got the velocity function, but we can derive it from the acceleration function by integrating. So this is non-constant acceleration problem, isn't it? So if we integrate that, then we're going to get this. We've got a constant integration to resolve, but again, we are told that it starts from rest. So when t equals 0, v equals 0. Another, a sort of obscure sort of boundary condition is embedded in the narrative of the question, and we need to make sure that we can glean these things out of the question. Not too difficult in that case. Sometimes they're a bit more obscure, and this is a very common one. Starts from rest at a fixed point O. In fact, starts from rest means this boundary condition, t equals 0, v equals 0, and starts from rest or starts at a fixed point O basically is t equals 0 and the displacement is 0. We're taking O as being our reference point. Okay, so anyway, that's going to give us that c is equal to 0. So our velocity function is simply this. And now we're looking for the points in time where the velocity is 0. And that's so if we just equate this function to 0, factorize it, we're going to get this. So that's going to give us solutions t equals 0, and this part will be 0, or t equals 10, where this factor in brackets will be equal to 0. So it's between 0 and 10. Let's just compare that to this. Well, that's what they've said, but they've said 10, they've said k. So k is equal to 10. Right, find the maximum speed of the cyclist. Well, at the maximum speed, maximum, it's all turning points, stationary points, isn't it? So, and in actual fact, the acceleration is going to be 0. dv dt is equal to 0. That's the acceleration. So, so in other words, this is our acceleration function. So if acceleration is equal to 0, then this term is going to be equal to this term, and we can just work that through and solve for that, and that's going to basically give us t equals 10 over 3 meters per second. All right, and there we go. So find an expression for the displacement of O from O in terms of t. Right, so that's the displacement. So to find the displacement, we need to integrate the velocity function. This is the velocity function. We integrate that. We got our constant of integration. And we use our other boundary condition, which is from this same bit of the sentence here, at t equals 0, s equals 0. And that implies, therefore, that c is equal to 0. So simply our displacement function is this function here. Okay, so that's that. I haven't actually done the last part. Find the total distance travelled by the cyclist from the time at which she reaches her maximum speed until she comes to rest. Okay, well, I'm not working that through, but that's something perhaps you can just finish off. Right. Right, so this one is conservation of momentum. Again, principles fairly straightforward. Sometimes the problems are not totally straightforward. A bead A of mass 0.1 kilograms is threaded on a long, straight, rigid wire inclined at this angle. the sine of it being 7/25, to the horizontal. Release from rest moves down the wire. The coefficient of friction is mu. When A has traveled 0.45 down the wire, its speed is 0.6 meters per second. Show that mu equals 0.25. Well, in this first situation, it's on the second part, it's conservation of momentum. We've got no collisions happening on this first part. So what have we got? I mean, we've been told about the mass, so we're going to suspect that this is, it's not going to be purely kinematics. Yeah, there's acceleration involved. The acceleration is due to this thing falling down here. So let's have a look at our free body diagram, our forces diagram. So we've got the result part of the weight coming down the slope, which is 0.1, that's the mass, times g. So that's the weight of it, but sine times sine theta is resolved down the slope. So I'll call that FA. The resolved part perpendicular is 0.1 g cos theta. Okay. So therefore that's what the normal reaction is. Got no other forces acting perpendicularly, so that must be the reaction force. And then we've got friction. Well, we don't know the value of friction, but we do know the reaction force, and it's mu that we're trying to find, isn't it? So let's have a look. So if we apply Newton's second law of motion to this bead coming down here, then what we've got is that the force acting down here minus the force acting upwards, back upwards, which is the maximum friction, is going to be equal to the mass times the acceleration. So we can substitute our FA, and our friction is going to be mu times r, and r is this. So that's going to be the friction there. And that's going to be equal to the mass times the acceleration. Okay, so all right, so we've got this equation with mu and a in it. But we can find the acceleration from as a constant acceleration problem. And in this case, we're looking at the final velocity here. It starts from rest, so u is equal to 0. We've got 2as, well, 2, that's the 2 times that's the distance it's traveled, and this is the acceleration. So we can work out the acceleration to be 0.4 from that Suvat's equation there. So if we substitute that 0.4 back into this equation, the 0.1s go out, a bit of manipulation, follow that through. That's going to, yeah, we know what sine theta and cos theta are. Sine theta is 7/25, and from that we can deduce that cosine of theta is 24/25. So Pythagorean triple, 7, 24, 25. And that's just going to give us that the coefficient of friction is 0.25. Okay, so that is part A. Right, now another bead of mass 0.5 is also threaded on the wire. At the point where A has traveled 0.45 down the wire, it hits B, which is instantaneously at rest on the wire. Means at the point it hits it, it was at rest. A is brought to instantaneous rest in the collision. The coefficient of friction between B and the wire is 0.275. Find the time from when the collision occurs until A collides with B again. Right, okay. Now, the reason this is part 7B in a 7-question mechanics paper is we just got to be able to visualize what's going on here. So basically, we've got one bead coming down, hitting this one here. This one starts moving. This one as a result of the collision stops, but because it's still got the same forces on it as if it was, as it had before the collision. So this is going to, this A is going to start moving again. In actual fact, they're only going to collide again if it's actually accelerating at a greater rate than the particle that's hit. So a bit of a kind of odd thing, really, but that's the basic idea. So let's have a look what happens. First thing we want to know is what happens to B when it sets off, when it kind of receives this kind of impact from A. And we can apply the principle of conservation of momentum to this. So basically the total momentum. So the momentum of A, which is the mass times velocity before the collision, plus the momentum of B, is equal to the momentum of A after the collision and the momentum of B after the collision. Well, we know the mass of A is going to be 0.1 and the velocity before the collision is 0.6. B is not moving, so that's going to be 0. After the collision, A is not moving, so that's 0. And B, which has a mass of 0.5, has got this velocity. And this basically is just an equation in VB2, because it's after the collision. Okay, so we can work that one through. That's going to give us that velocity is 0.12, velocity of B after the collision. Right. Okay, so well, so what's the acceleration of B going to be? We know the initial velocity, don't we? But we don't know where it's going to accelerate. It's not going to have the same acceleration as A because we've got a different coefficient of friction. So let's have a look. So yeah, if we're just looking at this is Newton's second law of motion, I might just kind of add that into there. So the downward force, which is the resolved part of the weight down the slope, minus the resistive force, which is friction, but we don't know the friction on its own, but we do know the coefficient of friction and the resolved part of its weight down the slope, which is 0.5 g cos theta. Okay, so so therefore that's going to be equal to 0.5 times the acceleration. Oh, right, okay, so we kind of glue all that together and we work out the acceleration of B. Yeah, we know theta, don't we? We know mu B. So we can plug all those values in and we're going to get 0.16. Okay. I'll just go back to this, by the way. We've got cosine theta there. So did I say it was the resolved part? This is the normal reaction. This is the coefficient of friction times the normal reaction. So let me just correct myself there. So that's the coefficient of friction times the normal reaction, and that is the friction. Okay, so resolved part of the weight down the slope minus the friction equals the mass times the acceleration. Okay, so that's the acceleration. Okay, so well, let me just a quick observation. So that acceleration is 0.16. This acceleration is 0.04. Okay, but of course, A is now starting again from 0 meters per second, whereas B has kind of got a head start because as a result of the impact, it's got kind of instant velocity of 0.12. So the two collide when the displacements of each of those particles after the collision are the same. Right, okay, again, another sort of theme that crops up in these kind of problems. Collisions happen when when the displacements are the same, sometimes when the time is the same. So we're going to set up an equation for the displacement, in this case the displacement of each of them. So the displacement of B is going to be given by this is S equals ut plus half at squared for for B, and that's going to be equal to the sort of similar expression. Now, we've got different B's, different initial velocities. Yeah, because we just worked out that 0.12 from B. And the acceleration we've worked out from here. In the case of A, the initial velocity is 0 because it kind of stopped as a result of the impact. And then its acceleration there, which we calculated before. And it's still 0.4. Regardless of the fact it's actually kind of stopped, it's still carried on with this. It's still got the same acceleration after that point. Right, so okay, so we plug our values into here, and we're effectively just left with an equation with t. Well, it's a quadratic, but it factorizes quite easily into this 0.12t into t minus 1. So that's giving us two solutions, t equals 0 and t equals 1. Okay, so t equals 0 is the moment of impact, and t equals 1 is the other occasion, at the moment of impact. Then the two displacements are the same, and then 1 second later they're the same again. So it takes 1 second before the second impact. Right, okay, so that's quite a nice little problem, and not an unusual type of problem where we're getting things that have two impacts. In this situation, it's because the accelerations are different. Sometimes we'll find a particle that goes up a ramp and then comes back down again and collides. Those are more complicated. So I hope we found that's clear as to what's going on. It's rather difficult to draw a diagram of this sort of thing. I think that's one of the problems, and as I said, it's visualizing what's going on, I think, which makes it a bit tricky. But hopefully that has been clear. I hope it's been helpful, and thanks for watching.